Okay, let's make a start on question 1. So it says, in this experiment you will investigate the equilibrium position of a pulley system. And then they start off where the equipment has been set up in a way that it's not ready to actually do the experiment. So you have to set it up so that the rods of the stands are approximately 50 centimeters apart, and we've drawn that on there. And it says adjust the pulley fixed to the stand so that the top of the pulley is approximately 60 centimeters above the bench. So the top of the pulley is there, so that means that we need to make this distance here 60 centimeters, and then adjust the boss holding the nail so that the nail is approximately 60 centimeters. So the nail is there, and that needs to be 60 centimeters. Now, whenever they say approximately, don't do it roughly, do it to as close as you can get it to 60 centimeters. So that's what I'm going to do now. Okay, that's as close as I can get it. So let's move on to the next part. It says, use some of the slotted masses to add a mass of 70 grams to Q. So if I look here, Q is the pulley side, so I need to add on there plus 70 grams. Now it says to add a mass of 70 grams, so I need to increase it on there. It doesn't say to remove Q or anything, so I'm going to take what I've got here. Maybe 50, 60, 70. Record the value of X. So it says the mass added to Q is X, record the value of X, so X is 70 grams. That's going to be I've already got grams there, so I'll just put 70. This is just to really the 1 sig fig because I've only got 50 gram and 10 gram masses. Then it says the angle between the plumb line and the string is theta, as shown in figure 1.1. Measure and record theta. Alright, so as you might have seen there, I had to get Mr. Rowland in to help because we both got a little bit stuck on this one. And this is something that can happen in the actual practical. Remember, we as teachers, we don't see what you actually have to do with it, so we try and give you the equipment as best we can. But for this question, the confidential instructions didn't even have this diagram. So, a couple of changes I've needed to make in order to make it work. First, I have to turn this nail around, because if we look at the instructions, you can see the nail is actually on the other side of the stand. And this pulley, this distance here between the pulley and the clamp stand isn't defined in the paper. So what that all leads to is a little bit of ambiguity. So when I said measure it to exactly 50 centimeters here, measure these to be exactly 60 centimeters. Well, it turns out in this instance it doesn't actually matter because there's already ambiguity of where this is going to be, there's ambiguity of how big this boss is. It really is just a make it up as you go along kind of thing. But that doesn't change my general advice, always check. Now in this instance, this happens to you. The reason I had to get Mr. Rowland in was basically this was hitting the table every time, no matter what I did. If that happens, put your hand up, we will come and help you. We sorted it out. In the real thing, we'd basically take and say, okay, you put your hand up at this time, we got it sorted at this time, we will give you that much extra time at the end of the exam, and we'll write a note to the exam board to say we were having to modify the equipment for you, and that's why you lost time. You're not likely to lose any marks for that because it's not your fault. It's a limitation in the way that we as a school have interpreted the instructions for you. Okay, let's carry on then. So I've added my 70 grams, and before I put 53, but I was alarmed by that because I wrote 53 with this Q hitting the table, and that seemed wrong. So I got it fixed, so now I can neatly cross through there, and I'm going to re-measure this angle. So we need to go from the plumb line to here. That angle, pretty much 70 degrees exactly. Okay, carefully remove the slotted masses from Q. Okay, part B. By using different numbers of slotted masses, vary x. For each value of x, measure theta. Repeat until you have 6 sets of x and theta. Record your results in a table. Include values of 1 over cos theta in your table. So these are the masses that I have been given. So I can go up to 240 grams, and the minimum I can do is 10 grams. Now, most people on this lost a mark because they didn't do a big enough range of results. Whenever you go to take your own data, it is vital that you use as wide a range of results as you possibly can. So I'm going to start filling in this table. We always do the variable and then the units for it. And the smallest I can do is 10. So let's put 10 grams in there. The biggest I can do is 240 grams in there. Now, there's different ways you can do this. My suggestion is always do your biggest and smallest, take those readings, plot on your graph the biggest and smallest, and then work backwards along here to try to get nice, evenly spaced results. That way you'll kind of get a decent scatter graph. So I'm going to do x in grams. I'm asked to measure theta. Theta is measured in degrees. I've already done 70, so I can include that from previously when I did 70 grams. I got 70 degrees. And then I'm asked for 1 over cosine of theta. Now, cosine of all trigonometric functions are just ratios, so there's no unit there, so I don't put a slash anything. I just leave that blank. In terms of significant figures, when you take a trig of a function or something, trig compresses a result, so you're allowed to go to one more significant figure along here. Right, let's get collecting some data. So, at this point, I'm now going to actually start plotting my graph. There's a couple of really good reasons for doing this. If you are plotting your points as you go on your graph, that means you're going to really quickly spot an anomalous result. In terms of actually sorting out my scale, I know I need to go up to 240 grams, so I have been told to plot a graph of 1 over cos theta on the y-axis, so that's going to go there. Again, that is dimensionless. Against x on the x-axis, so that will be x in grams. Okay, so here are my first 3 points. I can see 1, 2, 3. They're already lying on a line, which is pretty reassuring. And I want to try and fill in these gaps as much as I can. So it looks like there's a gap here for me, around about 160 grams. So I'll start with that one. Now that looks a little far from my what would have been my trend. So let me just check that again. I was supposed to have 160 grams. 5, 10, 15, 160. I'm going to recheck. Yeah, it's actually more like 77 degrees. So, this is why I suggest plotting your graph as you go. Because I can see straight away, well, that doesn't look quite right. This is why we use a pencil. So I'm using a pen so it shows up more easily. You would need to use a pencil for this. That's actually coming up as 4.44. Yeah, that's more in line. So good. Glad I did it that way. I need to get up to 6 sets. So let's just carry on with this. Okay, 6 sets of results. There we go. So I've plotted my graph, and I need to draw a straight line of best fit for it. Now I suspect I'm going to lose a mark here, because again, looking at this, I've got 2 results that don't sit very nicely here. Kind of go for some results there or results. No, actually, do you know what? This is probably going to be close enough for me. About half above, half below, and in the same direction. I'm going to go for that as my line of best fit. Okay. So let's get some marks so far on what I was supposed to do. First thing I was looking for was value of theta in the range of 50 degrees to 75 degrees. So yes, good, I get the first mark. 6 sets of readings of x with different values and theta in the correct trend. As x increases, average theta also increases. And yes, that is what my results do. There's a mark for the range of x min. It must be less than or equal to 20 grams and over 200. So that's where I was saying, whenever you do a practical like this, you must make sure you use the biggest and smallest possible values you can. Column headings, quantity and a unit where appropriate in the slash format. Must be no unit there. Now for here, you're measuring an angle, so that must be to the nearest degree because your protractor only measures to the nearest degree. Some of you put 0.0 at the end. That's just wrong. You can't do that. Significant figures, all the values of 1 over cos theta, same number of significant figures, or 1 more as number of significant figures in theta. So that means to all to 3 sig fig really. And then a mark for checking the calculation. When it comes to plotting the graph, so your axis must be labelled with the quantities. That's why I put the units. Scales must be chosen so that plotted points occupy at least half the grid, so half the distance in x and y. Sensible markings no more than 1 large square apart. Weirdly, a lot of you, large number of people, you kind of did every other square. So you did here, sorry, you did here, then here, then here. You're never going to get a mark for that. This has been on the mark scheme for years and years. Every large square at least labelled. Sensible scales must be used, scales must not be awkward. So generally, basically, no irrational numbers for what each, no irrational numbers per small square. It's kind of an easy way of thinking of it. Really, I would say 1, 2, 5, or 10. Sometimes you can get away with that. So I've technically gone up in 4 per big square, but I did that by labeling, going up in my sort of medium-sized squares and 20s. Plotting of points. All observations in the table must be plotted on the grid. Diameter must be less than half a small square. Now, that's if you're doing dots, but you would be insane to do dots. Always do nice, neat crosses. Then the last one, for the quality. The trend must be correct, which mine is. It must be possible to draw a straight line that is within plus or minus of 0.2 on the 1/x axis. Now, I'm not going to get that mark because, for instance, here, that's greater than 0.2 as a distance. And to be honest, I think almost everybody dropped that mark. I'd be very surprised to see if anyone managed to get that as perfectly done without, to be honest, cheating. This is when you're measuring angles, you get a very small change in angle, gets you a big change in cos theta. So it's unlikely you're going to get that quality mark. It's not the end of the world. Don't worry if you didn't get that, because this was a tricky one. It's generally better to work quickly and get through it efficiently than it is to fret over getting it perfectly. Okay. So we've worked now up to here, and we said we get 5 marks on here, then a mark for the column headings. This is how I marked it on your paper, so you'll see me going down like this. Mark for the column headings being correct. Mark for the range of results. Mark for all values of theta. Mark for significant figures. Mark for the calculation. So I would get 10 out of 10, well done me. On the graph, mark for the axes being labelled with a unit, and again we'll just do ticks down the side here to show you. Plotting of the point, I've done that. Quality, I don't get that, so I get 2 marks here. Draw a straight line of best fit, so it must be a good line of best fit. You'll see if you got that or not based on the mark. Now, determine the gradient and y-intercept of this line. When you're asked to do that, you must draw a large triangle and you must use your full line of best fit. So I'm going to start up at this end, and as I look down here, I'm looking for a coordinate that it goes through perfectly, and you always pick the first one, and there I can see straight away right at the top here, I have a lovely point that it goes through. This is 280 here. So that coordinate is I write the coordinate in there, and I do exactly the same thing at this end. I start down here and I work my way up until I find it going perfectly through a point, and I'm going to choose that one, and that plot point is now what I recommend you then do, well not recommend, what you must do is then draw how you're finding delta y and delta x on there. Okay, so now I'm going to take these coordinates that I've used and I'm going to plug them into the form. Gradient is change in y over change in x. So my change in y, it goes from 7.0 to 2.5. And that is divided by my change in x, which is from 296 from 56. Bash that into a calculator. And that comes out as 0.0214. And I can give that to 3 sig fig because I've got 3 sig fig down. Well, I've got 2 sig fig, 2 sig. Do you know what? I'm going to say actually 2 sig fig is probably better. So my gradient is 0.021. Y-intercept, I can just read it off my graph in this instance, which for me is 1.55. If you hadn't started your graph at 0, which is completely fine, you don't need to start your x-axis at 0, then I'd use the form y is equal to mx plus c, and I'd use that coordinate that I found earlier. So I have a coordinate written down, so I would say that my y is 2.5. That is equal to the gradient that I just found, so that's 0.21, multiplied by the x coordinate, which is 56, minus c. So c would be 2.5, take that away, so that becomes, take away 0.21 times 56, let's have a look. So it should be 0.021, there we go. I don't know why I was getting a funny answer. So that comes out as 1.32. So two different ways of doing it, both completely fine, depending on how you've set out your results. Obviously, I'm not going to do it that way. I'm just going to read straight off of my graph. So now they tell you, it is suggested that the quantities theta and x are related by the equation 1 over cos theta is equal to ax plus b, where a and b are constants. Use your answers in C part 3 to determine the values of a and b. Well, 1 over cos theta, that was what was on my y-axis. X was on my x-axis, so therefore a must be the gradient, c must be the y-intercept. So numerically the numbers will be exactly the same. A will be 0.021 and b will be, for me, 1.55. However, these are constants. Constants are physical quantities, so they must have a unit attached. So I need to figure out, well, what is the unit for a? Well, I found my gradient by doing 1 over cos theta, that's my y-axis, so sort of units-wise, I said that gradient is change in y over change in x. Now, change in y, that is 1 over cos theta, take away 1 over cos theta, so that is dimensionless. Yeah, nothing to do with it. But I've divided that by something that is a change in grams. So therefore, that becomes grams to the negative 1. Right, so that's going to be my unit for the gradient, no unit for b, because b is just that. Let's think if that makes sense. I know that 1 over cos theta must end up being dimensionless. Well, b is dimensionless, so that's fine. I'm adding something dimensionless, so I need to make a times x dimensionless. X is in grams, so to make a, again, turn this term dimensionless, I'm going to have to do inverse grams, or grams to the negative 1. So again, there's lots of different ways you could have got there, but whatever happened, when you're asked for this bit, when you're asked to find a constant, constants should have appropriate units in them. Okay, the mass m is m, and the mass of q is q. The constants a and b are related to m and q by these two equations. Calculate the value of m and q. So it's pretty straightforward. I can say for a is equal to 2 over m. I know a, so if I substitute in, I can say 0.021 is equal to 2 over m. So m is equal to 2 over 0.021. Put that into my calculator. And I get, ooh, well done me. I get 95 and this is to 2 sig fig, so I should really give us an answer just to 2 sig fig, 95 grams, which is pretty good because you can just look at the equipment and you can see that these are 100-gram mass hangers. So if they're 100-gram mass hangers, it should be 100. So I'm pretty pleased with that. Go back to the paper. Q, well, I've got B is 2Q over M. So I've now got a value for M. So if I rearrange it, I can say that Q is equal to B times M over 2. So that is 1.55 times M, which is 95, divided by 2, which I think is going to be a little bit further away, but not surprising. Let's do that. Let's multiply that by 1.55, and then divide it by 2. Yeah, so I get 74 with rounding there, which again, not too far away from the real value, actually, considering this is a pretty tricky practical to do. Let's go back to our mark scheme and just check what you were actually asked for here then. So, line of best fit. Best fit is judged by balance of points around the candidate's line, no kinks, no thick and small, half small square. Don't do an anomalous for points. If you get an anomalous result, go back and redo it anyway. Gradient. So we need a biggest triangle possible. They say greater than half the length of the line, but really, like I say, just make it as big as possible. We look for the read-offs being correct, the calculation correct, and the gradient sign must be correct, consistent with it, in other words, positive line. What you'll notice actually is that these sections, they are identical year on year on year. This doesn't change at all, so you know exactly what you're going to be asking for. Y-intercept again, correct read-off or substituted in. For part D, so we're saying that A must be the gradient and B must be the intercept, must be given to significant figures. Correct unit, which is grams -1 and no unit for B. And then correct calculation of Q. If you manipulated it, you could just do, I think it was B over A also worked, and that was another way of checking it. Obviously, you might get a slightly different answer with rounding, but that's what we were looking for there. So, that's your paper finished. A couple of kind of general points that I would suggest, things that came up again and again, and that will come up on every year's papers. One, check your setup of your results. If you're getting things like this hitting the desk and things that don't work, put your hand up, ask us, it's fine, these things happen. In terms of actual accuracy of taking your readings, I really suggest that you plot a graph as you go. You need to choose the biggest possible range anyway, because there's nearly always a mark for whatever your independent variable is. In this case here, it's these masses. There's nearly always a mark for getting the biggest range you can. So it just makes sense to say, well, they will only ever give you a straight line graph. It's never going to be a curve, because for the paper, for question 1, you've always got to figure out a gradient. So if you end up with a curve or something like, anything really where your independent variable aren't in a straight line, something is wrong with your experiment and you need to go back and check it anyway. So if you take your two extremes of your independent, whatever you're supposed to be plotting, that should be one end and other end of the graph. And obviously it could be up here and up here, but you're going to get those two ends. So then it's quite easy to plot as you go. That's going to, like I did here, that's going to pick up your anomalies for you a little bit more easily. Then when it comes to the actual paper, make sure that you are drawing a nice line of best fit, that you draw the gradient and the coordinates for that gradient into there. And after that, it's all just maths. So I hope that's useful. Do come and see me if there's anything else you want to ask me about.